Welcome to the class. Dear students, today we are going to see stereoselective reduction of alkynes. In the first section of the video, we will see the feasibility of the conversion of alkynes into alkenes and alkanes. And then we will see the mechanism of the hydrogenation of alkynes. Then we will see the total reduction of alkynes. This will be followed by the partial reduction of alkynes, in which we will see two methods. The first is the catalytic hydrogenation of alkynes and the second is the dissolving metal reduction. We will see the reaction and its mechanism and then we will go for its summary. So let us start stereoselective reduction of alkynes. So here we will start with the introduction part. Alkyne is unsaturated hydrocarbon with the triple bond. Alkyne is unsaturated hydrocarbon with triple bond. It has got 1 sigma bond and 2 pi bonds. The energy required in the formation of 1 sigma bond is 83 kilocalorie per mole. And the energy required in the formation of a pi bond is 63 kilocalorie per mole. So obviously the sigma bond is thermodynamically lower energy or thermodynamically much stable than the pi bond. That means alkanes are thermodynamically stable than alkene and alkene are thermodynamically stable than alkyne. So therefore it is thermodynamically feasible if one pi bond breaks and 2 sigma bonds with hydrogen forms. Right? So the formation of alkene from alkyne and the formation of alkane from alkene is thermodynamically feasible process, because in this process more energy is released and more stability is obtained in the molecule. So that means the reaction here, that is a hydrogenation, is a thermodynamically feasible process because more energy is released when 2 sigma bonds are formed rather than a breaking of 1 pi bond. Correct? So it is a thermodynamically feasible process. Okay. The second question is, then what is the mechanism of reaction of hydrogenation? Correct? So you know alkyne has got a double pi cloud. Alkyne has a double pi cloud because it has got 2 pi bonds. It has a double pi cloud. Any electrophile that comes along its way is engulfed in the pi cloud. It is engulfed. Look at this. It is engulfed in the pi cloud. This gives the pi cloud a positive charge. Now this electrophile takes the pair of electron from one of the carbon atom. Okay. Assume that it has taken the electron pair from this carbon atom. In that case, it leaves a positive charge on the adjacent carbon atom. There occurs a positive charge on the adjacent carbon atom. To this positively charged carbon atom, in the second step, a nucleophile attacks. And the result is an addition product or an adduct. The result is an addition product or an adduct. The whole sequence of this addition reaction actually started with the attack of the electrophile. That is why this reaction altogether is called as electrophilic addition reaction. Electrophilic addition reaction is the distinctive reaction shown by alkenes and alkynes. It is the characteristic reaction that is shown by alkenes and alkynes. Hydrogenation is an example of electrophilic addition reaction. In place of electrophile, the H plus gets engulfed in the cloud. It is the H plus that gets engulfed in the cloud. In place of the electrophile, H takes away the pair of electron from one of the carbon atoms, leaving the other carbon atom with a positive charge. Now, taking this opportunity, the hydride ion comes and attacks the other carbon atom, resulting in the formation of alkene. Therefore, the hydrogenation of reaction is the electrophilic addition reaction. Dear students, now in this section, in the first section, we have seen that it is thermodynamically feasible process because more energy is released if alkyne is converted into alkyne is converted into alkene, because alkene is more stable than alkyne. Okay, and we have also seen the addition, electrophilic addition reaction, how hydrogenation of alkene is electrophilic addition reaction. We have seen this in the first section. Now let us go for the reduction of alkene, reduction of alkyne. So there are two kinds of reduction that alkyne shows. One is total reduction of alkyne. Total reduction. Let us see what it is. Total reduction of alkyne. So here I am taking an alkyne. This is acetylene, an unsubstituted alkyne. Just hydrogenate it. Okay, take the solution of the alkyne in ethanol and go for pumping of hydrogen gas at 3 to 4 atmospheric pressure. Okay, take any catalyst like nickel, Rani nickel. So if you are taking nickel, you have to heat it, or otherwise if you want to save energy, rather than taking nickel, go for platinum or palladium. No heating is required in that case. And now what would happen? It will convert itself into alkene in the first step. In the first step, it converts itself into alkene, and this alkene further it converts itself into alkane. So that is a total reduction, or reduction in the normal way. Okay, normally this is what happens if you try to hydrogenate alkyne. So here, when alkyne is reduced, it is obvious that alkane will be formed in the final step. You cannot stop this reaction to get alkene. Okay, you cannot control this reaction to get alkene. If alkene is formed, then alkane will be formed. You cannot get alkene in this reaction. Okay, even if you use a low amount of the starting material alkyne, you will get alkane. Even if you use a low amount of hydrogen gas, if you are using a low amount of hydrogen gas, you will get a mixture of alkene and alkane. That means the yield of alkane will be less, but there is no question that you will get alkene. Even if you use a low amount of catalyst, you will get a mixture of alkene and alkyne, and there is no question of getting alkene. That means in any way you try out this reaction, you will not get alkene. You cannot control this reaction to get alkene. Whatever alkene is formed converts itself into alkane. So that is a limitation of this reaction. Okay, so we want alkene in our hand. So what do we do to get alkene in our hand? So for that, you have to carry out partial reduction of alkyne. Partial reduction of alkyne. If you are carrying out this, you will get alkene. So for carrying out this, there are two methods. Okay, two methods are there. First method is catalytic hydrogenation. Catalytic hydrogenation method. And the second method is metal reduction, dissolving metal reduction. So if you use these two methods, you can go for the preparation of alkene from alkyne. You will get a control over the reaction. Catalytic hydrogenation and dissolving metal reduction. Now I want to add that not only will you get an alkene, but you can have control over the geometry of the alkene. What I am going to say is the partial reduction of alkene, it is also called as stereoselective reduction of alkene. It is also called as stereoselective reduction. Why it is called as stereoselective reduction? Stereoselective reduction is a reduction in which one isomer predominates or overweighs the other isomer. I repeat, stereoselective reduction is a reduction in which the one isomer predominates or overweighs the other isomer. In catalytic hydrogenation, cis isomer predominates. Cis isomer is the formed isomer. And in dissolving metal reduction, you will get the trans ethene or the trans isomer of the alkene. Okay, so in catalytic hydrogenation, cis isomer predominates. In dissolving metal reduction, trans isomer predominates. Therefore, both the methods of the partial reduction of alkene, both the methods are stereoselective reduction methods, because in this reduction methods, only one isomer predominates. In catalytic hydrogenation, cis predominates. In dissolving metal reduction, trans overweighs or trans predominates, and only trans alkene is formed. Let us see our reaction and mechanism, and then we will understand why cis is formed in catalytic and trans is formed in dissolving metal. So first we are going to discuss catalytic reduction. Catalytic reduction. Number 1, catalytic reduction. Let us see what is happening in this reaction. So you are going to take a substituted alkyne, so that you get to know whether it is cis or trans. Okay, you can easily identify if you take a substituted alkyne rather than acetylene. So you are going to take a substituted this thing. Okay, alkyne. So there you go. Okay, now you go for its hydrogenation with in presence of Lindlar's catalyst. Lindlar's catalyst. If you do that, you will get your cis alkene in your hand. Cis alkene in your hand. This is 2-butene, right? This is 2-butene. Now you are getting here, this is 2-butene. Okay, so now you are getting here a cis alkene. The important thing is the geometry of the molecule. You are getting here the cis alkene because H is on the same side of the molecule, right? It is below the plane of the molecule, so it is cis-butene, correct? Now let us see what is Lindlar's catalyst, and then we will go for the mechanism of action. Lindlar's catalyst is Lindlar catalyst. It is your quinoline, okay, and for dissolving quinoline you need to have lead acetate. You need lead acetate, so you dissolve quinoline in lead acetate. So that's it, lead acetate. Okay, and you need the metal palladium in 5% calcium, 5% palladium in calcium carbonate for dissolving palladium. Okay, for dissolving this you need lead acetate, and for dissolving palladium you need calcium carbonate. So that is the Lindlar's catalyst. So it is basically palladium that has been poisoned by quinoline. Okay, see, quinoline is having a lone pair of electron in nitrogen, so it can donate the lone pair of electron to palladium atom, because palladium atom has got empty orbitals. Okay, it has got empty orbitals. It has got orbitals with unshared electrons. Okay, so it can accept electron from quinoline. It can accept electron from quinoline. So most of the spaces of palladium metal are occupied by quinoline. So there are only few sites where hydrogenation can take place. So what we have done here is that we have reduced the effectivity of the palladium catalyst as a catalyst. We have reduced the spots where the hydrogenation can take place. We have reduced the efficiency of the catalyst. How? I have already said. See, actually what is the funda here is that it accepts the pair of electron from quinoline, from the nitrogen, because palladium is having empty orbitals which have unshared electron. So it can accept electron from nitrogen, because of which most of the space of palladium is occupied by quinoline. So there are only very few spots where hydrogen can attach or where acetylene can attach and hydrogenation can take place. Okay, so hydrogenation power is limited. Okay, so the efficiency of the catalyst has been reduced by using Lindless catalyst. Okay, let us now get a better understanding. We have to see the mechanism of action. So let us now go for the mechanism of action. Here it is clear, I hope. We are getting a cis isomer, right? Now we are going to see why we are getting a cis isomer. Fine. Okay. So let us see the mechanism of action of catalytic reduction. There are 3 steps. Step number one, addition of hydrogen. Addition of hydrogen to metal surface. Hydrogen to metal surface. So we have got palladium metal here, correct? And hydrogen, we are pumping hydrogen. So hydrogen is coming near to the metal surface. Fine. Now what would happen? Yes, hydrogen would go for attraction. There is electron, 1 electron in hydrogen, right? So hydrogen will try to give its electron to palladium. Why? Because the palladium is having empty orbital, which has having the orbitals of palladium or platinum, they are having unshared electron in their orbitals. So it can easily accept electron from hydrogen, okay, and become stable. So now there is an attraction between hydrogen and palladium, and finally palladium is able to capture the hydrogen and make bond with it. By accepting its electron from hydrogen, it makes a bond with hydrogen. So now it has made a bond with hydrogen. Fine. So that is the first step, the addition of hydrogen to metal surface. This is because palladium is having empty orbital. It is able to accept an electron from hydrogens. Okay, it is having orbital in which there is unshared electron. So it is able to accept electron from hydrogen, and finally it makes a bond after acceptance. This is the first step. Now let us go for step number 2. Step 2, adsorption of alkyne on metal surface. Let us see what happens here. So this is the palladium metal, right? And this is our hydrogen, which is attached to palladium metal, because hydrogen has donated an electron to the orbital which had unshared electron. So therefore hydrogen has formed a bond. Now as we know, our alkyne also has is a very good source of electron. So palladium will have a natural attraction to take the electron of alkyne, correct? Because alkyne is also rich in electron. So palladium will also gain a natural attraction to attract the electron pair from the alkyne so that it can fill its orbital. So that is what it is shown here. There is an attraction, and mind you, this is an attraction, not a bond. Okay, this is only an attraction, not a bond. This is only adsorption. Okay, so it's only on the metal, this thing, there is an attraction, right? So here is that attraction that has occurred, and because it is an attraction, it is relatively farer from the surface of palladium than hydrogen, because hydrogen is a bond. So it is nearer to the surface of palladium, nearer to the surface of the palladium, and because it is only an attraction, the interaction of palladium with alkyne is only an attraction, it is farer from the surface of palladium. Okay, this is the attraction, but alkyne won't give its electron to palladium. In no way it will do that, correct? In no way it will do that. So first let me complete the reaction. First it will come close here, and in the next step what would happen? This would occur. There is an attraction. So here we have seen first it is coming closer to the metal surface, and now here there is an attraction because alkyne is rich in electron. So palladium wants to gain electron from alkyne. So there is an attractive force, but in no way the alkyne loses its electron pair, because the loss of electron pair would mean instability to the alkyne molecule. But so in no way will it lose its pi electron pair, but of course there is an attraction, and because this is an attraction, it is farther from the surface of the palladium, and because this is not an attraction, this is a bond, it is nearer to the surface of the palladium. Fine. So it stays on top of hydrogen, right? Now let us see what happens in step number 3. Step number 3, addition of hydrogen to alkene. Addition of hydrogen to alkene. Fine. Let us see what happens. So as we have seen in this diagram, so this is with the hydrogen, and your alkene is on the top of it because it is farther from the surface, because it is only an attractive force, therefore it is farther from the surface. Now what can happen is this H hydrogen, it gets attracted to the pi cloud here, because the pi cloud is now dispersed here, it is directed towards the space here. The H gets attracted, H plus goes and attaches here. When H plus goes and attaches here, what can happen? This carbon atom, the adjacent carbon atom, may become positive, right? The H plus gets attached, gets engulfed in the pi cloud here. That engulfment produces a positive charge on the pi cloud, and in the next step the H takes a pair of electron from this carbon. The pi pair of electron is taken from this carbon, resulting in positive charge on this carbon. When a positive charge comes on this carbon, it takes H minus hydride towards itself. Fine. So now the end product is like this. Fine. So the product is a cis product because syn addition has taken place. Syn additions mean addition from below the plane of the molecule, from the same side of the molecule. If the addition takes from the same side of the molecule, it is referred to as the syn addition. SYN, syn addition. So here the addition has taken place from below the molecule, below the plane of the molecule. So it is a syn addition which has taken place from below the plane of the molecule, resulting in a cis product. That is, H is introduced from below the plane of the molecule. Dear students, we have seen that in catalytic hydrogenation we get cis product. This is because everything gets adsorbed. The hydrogen gets added onto metal surface, and this is because the alkyne gets adsorbed on the metal surface. The alkyne is relatively far from the metal surface than hydrogen. Hydrogen is nearer to the metal surface, and because of which the hydrogen, the two hydrogen gets added from below the plane of the molecule, resulting in the cis product. So this is the mechanism of catalytic hydrogenation of your alkynes. Let us go to the second method by which we can prepare alkyne, that is dissolving metal reduction. Second method, dissolving metal reduction. What happens in this? Let us see. Dissolving metal reduction. So in this reaction, let us see what is happening. We are taking a substituted alkyne, due to 2-ine we are taking. You are hydrogenating it in presence of sodium and liquid ammonia. What you get is a trans alkene. You get a trans alkene like this. Butene, yes, but trans 2-butene. Trans 2-butene. You get a trans 2-butene. So if you are hydrogenating alkene, you will get, if you are hydrogenating alkyne, you will get an alkene. Partial reduction does take place, but it is a stereoselective reduction where the trans isomer predominates. Okay, that depends on the catalyst that has been used. If you are using this catalyst, sodium and liquid ammonia, you would get a trans. In that case, that reaction will be called as dissolving metal reduction, because the metal is dissolved in the solvent of liquid ammonia. That is why it is called as the dissolving metal reduction. Dear students, we will see why the trans isomer is formed in the mechanism. We will understand it in mechanism. So here it is very clear. This reaction will give the trans isomer if the catalyst is changed. Suppose here it was Lindlar's catalyst, we would have get cis isomer. So it depends on the catalyst that we use, right? The stereoselective reduction depends on the catalyst that we are using. Let us now go for the mechanism. Mechanism. There are 4 steps in the mechanism. Step number 1. Step number 1. Donation of electron from metal. Donation of electron from sodium metal. Let us see what is happening. So this is our C. This is our H3. I am writing H3 here. Double bond C, CH3. Yes, I am going to write the triple bond, but in this way I am writing the triple bond. Suppose the upper lobe is having the electron right now. Okay. So this is the triple bond. This is just the pi cloud that I have shown. Now I will react it with sodium. Now sodium has got one electron in its outermost shell. It needs to get rid of its one electron to attain the inert configuration of your neon. So what will happen here? It will kick its electron into one of the into the p orbital of one of the carbon atom. So suppose it has chosen the orbital of this carbon atom, okay, to pump its electron. So what would happen here? We will see something like this. This orbital will have 2 electrons, correct? This is having, okay, correct? So we will see that here we have seen here that the sodium pumps its one electron to the p orbital of one of the carbon atom. Suppose it has pumped its electron to the p orbital of this carbon atom, then the p orbital of this carbon atom gets a pair of electron. An electron is there here. Okay, the pi bond has actually broken now. Fine. Now this is negative charge. So obviously if it is negative charge, it will try to become as far as possible because there will be repulsion forces, because of which this electron here, okay, it has a higher probability to go in the lower lobe. Correct? Here. Am I right? And what would happen? It will also go to the farthest position possible. So what would happen? This lobe would go here and this would go here, right? Accordingly its lobe direction will also be changed little bit here, and this also will be changed because it has moved, so it will be here, correct? This CH3 here, it will face repulsion forces, so CH3 may come down here and this CH3 may go upstairs because there is repulsion. So we are seeing a situation like this when you are treating it with sodium. Step number 2, abstraction of proton from step 2, abstraction of proton from solvent. So what is the solvent that we are using? Ammonia, correct? So now let it be here only. I am using dilute ammonia, right? So ammonia, I will write it like this, H NH2. Actually ammonia is basic in nature, correct? It has got a pair of electron. So it tries to donate electron. But this is a greater base. The carbon anion is a greater base than ammonia. When it encounters a carbon anion, ammonia actually acts as an acid. Okay, and it get rid of its H. The H plus dissociates, and that H plus it goes and attaches to this pair of electron. Fine. So now what we get is this. Right? I hope you got it. Ammonia actually is basic in nature, but in front of carbon anion it is acidic, because carbon anion is a very strong base. It has a tendency to donate its pair of electron. This is a very unstable condition for carbon. It has a tendency to donate its unshared, lone pair of electron. So what could happen is the ammonia, it acts as acid. It get rid of its H as H plus, and that results in NH2 minus. Fine, NH2 minus. Fine, and that H plus it goes and attach in the orbital, in the p orbital, and it takes up an electron. So that is how we get this. Fine, this NH2 minus it can join with your sodium plus, which was initially in the first step we saw, no, when there was a sodium, it kicked out its electron to become Na plus. That Na plus it can join and it can become NaNH2, no issues. Right, this NH2 minus can join with Na plus in the first step and it can make NaNH2. So that is the second step. Let's go for the third step now. Step number 3. Step number 3, donation of electron from sodium. Second donation. Okay, this is second donation of electron from sodium. So again what could happen, that the sodium, it can again, another sodium, it can again pump its electron to this orbital. Now what would happen? We get this. Am I right? Yes, there is a small lobe here. Yeah. Let me, yes. So again the sodium, it can pump its electron, another sodium, it can take its, to become stable, it can pump its electron to the unshared, to the p orbital of carbon atom that is having unshared pair of electron. So when it pumps electron, it may become Na plus comes out. Correct? Now fourth step, step number 4. Step number 4. Second abstraction of proton from sodium, sorry, abstraction of proton from ammonia, from solvent ammonia. Again the process may repeat. Ammonia, dilute ammonia. Ammonia is actually basic, I told you, but in front of carbon anion it becomes acidic. It gets rid of its H plus, and that H plus can go and attack this, and that results in, let us see what it becomes then. Yes, so we get a trans, this is double bond here in all of our reaction. So it now becomes a trans 2-butene. So we have got a trans isomer, trans alkene, right? So this is how, dear students, we are getting a trans alkene in dissolving metal reduction, which we have seen in method 2. We have seen here how trans alkene we are getting. In method 1, which we discussed earlier, that is catalytic hydrogenation, we got a cis alkene. Okay. Dear students, we have seen that it is not possible to reduce alkynes in normal conditions. in normal conditions we can reduce alkynes, but what we get is alkane. We could never get alkene. The only way to reduce alkyne to alkene is for going for partial reduction of alkynes, but the partial reduction of alkynes is actually a stereoselective reduction where one isomer predominates. That means we not only get a control on the synthesis of alkene, but we also get a control on the geometry of the alkene. Correct? The first method, catalytic hydrogenation, it produces the cis isomer. The second method, dissolving metal reduction, it produces the trans isomer. So we have a control over the geometry of the alkene now, and that is a very good advantage that is here before us. We have seen why cis alkene is formed. In cis alkene, everything gets attached to the surface of metal. Hydrogen is bonded to metal surface, while alkyne is attracted to metal surface. Mind you, only attracted. Therefore, the alkyne is above the hydrogen. Correct? The alkyne is relatively far from the surface of the metal than hydrogen. Hydrogen is nearer to the metal surface. With the result, alkyne is above and your hydrogen is on the bottom side. So when the addition takes place, it takes place at the from the below the plane of the molecule. Correct? So it's a syn addition that takes place, resulting in a cis product. Here we have seen that the negative charges are formed as intermediate on both the carbon atoms. These negative charge repel each other and go to the farthest position possible. In the first step itself, we have seen that the negative charges are formed in adjacent carbon atom. The negative charges formed in the adjacent carbon atom go to the farthest position available. The farthest position available is the trans position, and because of which, when the addition takes place, we get a trans isomer. Dear students, I hope you have understood and I hope you have liked the class. Your small act of subscribing this channel would be a great encouragement for me. Please do like and share the video. Thank you very much.